Hi everyone! This week we are going to talk about rockets and how we can use them to move a spacecraft in space. All this has to do with propulsion. To propel oneself is to create a force that will set you in motion or change your speed and direction, as dictated by Newton's second law over here. Newton also said, in his third law, that for every force that we create, the action, there must be an equal but opposite force, the reaction, acting somewhere else in the universe. In other words, we cannot just create one individual force to move ourselves. We necessarily have to move something else in the opposite direction if we want to move forward. In the case of a car, for instance, the wheels experience a force with the ground when the car accelerates. Here, the action and the reaction are the friction forces on the ground and the force on the car, which are always equal and opposite to each other. In the case of an aircraft, the jet engines are continuously swallowing a large amount of air from the atmosphere, and after burning fuel in the combustion chamber, discharging it at a much larger velocity through the nozzle. In this example, the action and reaction are the force exerted on the air and the thrust force on the aircraft. An important conclusion is that we always need an additional medium or body, here the ground for the car and the air for the aircraft, on which to exert one of the two forces. Exactly the same principle applies to everything else, like an air balloon that is deflating. Can you tell what is the reaction medium here? Well, in this case, it is the air that is leaving the balloon itself that acts as the reaction medium. As the balloon is accelerated forwards, the air is ejected and accelerated backward. We could say that the balloon carries its own reaction medium within and uses it up when it propels itself. If we want to propel ourselves in vacuum, where there is no ground or air that we can use, the only available option is to actually function like a balloon. That means we have to bring our own reaction medium with us, the propellant, and eject it as the opposite direction where we want to accelerate. This is exactly what a rocket does, and that is why rockets are used for propulsion outside of the atmosphere. For the same reason, they are our only means to launch something into space. Can you think of any other ways of reaching space that do not use rockets? A chemical rocket contains propellant materials that we can burn in an exothermic reaction and create lots of hot gas at high pressure. Then the hot gas expands and accelerates in a nozzle to form a high-velocity jet. This way of propelling ourselves has a major but unavoidable drawback. In the first place, we have to carry a lot of mass in our rocket, the propellant, only to throw it away later. In the second place, the engine is useless once all the propellant has been used up. At that point, we cannot propel ourselves anymore. Let us investigate now in more detail how a rocket works. Imagine that you are sitting on a rocket with a total mass m that is moving at a velocity v with respect to the ground. The total momentum of the system is p, t0, as defined over here. An instant later, the rocket ejects a chunk of mass, delta m, in the opposite direction, with velocity ve with respect to the rocket. Naturally, this will change your own velocity. Since the total momentum of the spacecraft and the propellant is conserved, the velocity of the rocket must now be v plus delta v. Observe that the velocity of the ejected mass with respect to the ground is v minus ve. Inspecting the equations 1 and 2 here, one finds that the velocity increase of the rocket depends on how much propellant we eject, and the velocity of the propellant and the instantaneous mass of the rocket, including the propellant that we have not ejected yet. Now, rockets do not eject mass in discrete chunks, but continuously as a jet. This is equivalent to saying that we eject mass in many tiny chunks of propellant continuously. Indeed, in the limit that the chunks are very, very small, we can write the mass ejected per unit time as the derivative dm over dt. This is called the mass flow rate, m dot, and it has units of kilograms per second. Lastly, if we take the previous equation and divide it by a small time interval, delta t, as in here, remember that the change of velocity per unit time is the acceleration of the rocket, so we can write this expression in the limit of a small delta t as so. This equation states that Ve times m dot is the thrust force that we get from our rocket. In reality, the equation is slightly more complicated than that, because there may also be a small additional contribution to thrust due to the pressure of the exhaust jet. Nonetheless, we may always write thrust in this form by defining a Ve as effective exhaust velocity of the jet, that is, including the pressure contribution. Now, observe that a high thrust force is obtained for high mass flow rate, m dot, and exhaust velocity Ve. However, if we have a high mass flow rate, we are going to use up the propellant pretty quickly. Therefore, if we want to use our rocket for a very long time, while providing a good thrust force, the only reasonable way is to increase the exhaust velocity as much as possible, while keeping the mass flow rate at a moderate level. So, in this video, we have seen that propulsion requires an additional medium onto which to exert a reaction force, and that a rocket carries its own reaction medium within it, the propellant, which is expelled continuously as a jet. The jet velocity is one of the main performance figures of the rocket,